In this video, we'll be going over an energy FRQ for AP Physics 1. A block of mass m is released from rest at position x equals 0 near the top of a ramp. The ramp makes an angle of theta with the horizontal. The block slides down the ramp with negligible friction. At x equals 8d, the block makes contact with an uncompressed spring with spring constant k. The spring is then compressed and the block momentarily comes to rest at x equals 12d. Figure 1 shows the instance when the block is at x equals 0, x equals 6d, and x equals 10d respectively. Part A. Figure 4 shows an energy bar chart that represents the kinetic energy of the block, the gravitational potential energy, UG, of the block's spring Earth system, and the spring potential energy, US, of the block spring Earth system at the instant that the block is at x equals 10d. The gravitational potential energy UG of the block spring Earth system is defined to be 0 when the block momentarily comes to rest at x equals 12d. Draw shaded bars that represent kinetic energy, gravitational potential energy, and spring potential energy to complete the energy bar charts in Figure 2 and Figure 3 for when the block is released from rest at x equals 0 and for when the block is at x equals 6d respectively. Shaded bars should start at the dashed line that represents 0 energy, represent any energy that is equal to 0 with a distinct line on the 0 energy line. The relative heights of each shaded bar should reflect the magnitude of the respective energy consistent with the scale used in Figure 4. This is a problem about mechanical energy. And in the problem, we read that there is no friction along this ramp. And so we know that there's no external net force doing work on the system, which means that the mechanical energy is conserved in this problem. So the total amount of mechanical energy at x equals 10d is going to be the same at all the other positions. If we take a look at Figure 4, we see that the kinetic energy that there is 7 e naughts of kinetic energy. For the gravitational potential energy, there's 2 e naught of energy. And for the spring potential energy, there's 3 e naught of energy. If we add 7 plus 2 plus 3, we get 15 e naughts of energy. So at position x equals 0, we should have a total amount of 12 e naught of energy as well. Now we know that the spring is not compressed at x equals 0, so there is no spring potential energy, and because the block starts at rest, that was we read that in the question, so there is no kinetic energy at x equals 0 as well. So all of the energy at the beginning here is going to be stored in the gravitational potential energy. At x equals 6d, we still do not have any spring potential energy because the spring is not compressed. But the rest of the energy is going to be split between the kinetic energy and the gravitational potential energy. The question is if it's going to be an even split or if it's going to be more of one compared to the other. So we're going to think through this a little bit. So here is a right triangle, and this representing the ramp. Here's the angle of the ramp. X is the ramp, I'm going to call the ramp distance, so the distance along the ramp, and h is the height. Now there's a relationship between this ramp distance and the height. Sine theta is equal to h over the ramp distance. If we solve for h, the height, that's equal to x sine theta. And so from this equation, we see that h is proportional to x. So we're going to use some ratios to help us think about the amount of gravitational potential energy at x equals 6d. So we know that when the block is at the very top, that is a distance of 12d from the bottom of the ramp. And at the top of the ramp, it has 12 e naughts of energy. And we figured this out when we were drawing the graph for Figure 2. And we're going to set this equal to 6d, which is the location that we're trying to figure out the gravitational potential energy of. And then on the bottom here is the gravitational potential energy at 6d. So I'm going to cross multiply, and I get 12d times the gravitational potential energy at 6d is equal to 6d times 12 e naught. Notice the d's cancel out, and so we see that at location 6d or position 6d, the gravitational potential energy is equal to 6 e naught. And so we're going to draw a 6 E naught of energy for gravitational potential energy because the total amount of mechanical energy needs to add up to 12 E naught. The kinetic energy has to be 6, so 6 plus 6, we end up with 12 E naught of energy. Part B, figure 5 shows the block at x equals 0 when the block is released from rest and the block at x equals 12d when the block momentarily comes to rest against the compressed spring. Starting with the conservation of energy, derive an equation for the spring constant K. Express your answer in terms of m, theta, d, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. So I'm going to create an LOL chart. This does not mean that you need to have created this for the exam, but I'm just using this to explain this problem. So here we have the initial energy. All of the energy is stored in the gravitational potential energy. And there is no kinetic energy because the block is not moving, and there's no spring potential energy because spring is not compressed. This is showing our system, which includes the block, the ramp, and the earth, and the spring. And here we're showing the energy after the block has traveled all the way down to x equals 12d. There's no kinetic energy because it's not moving. There's no gravitational potential energy because it's at the 0 line. And there is spring. All the energy is stored in the spring at 12d. And so the question that we're trying to figure out is, what is the spring constant? And so we're going to use the conservation of mechanical energy equation, which says that the initial mechanical energy equals the final total mechanical energy. And the initial mechanical energy is just the gravitational potential energy. The final mechanical energy is just the spring potential energy. And gravitational potential energy is mgh. Spring potential energy is 1 over 2 kx squared. Now next, we need to solve for h here, and we're going to go back to our triangle. And we previously used some trig to show that the height is equal to x, which I'm going to call the ramp distance, sine theta. And the ramp distance is 12d, so it's 12d from the bottom of the ramp. So on the left-hand side here of gravitational potential energy, we have big M, which is the variable they gave us, times g times 12d, that's the ramp distance from the bottom, sine theta, is equal to 1 over 2, and then this is the spring potential energy, 1 over 2 kx squared, so we have 1 over 2k, and the spring has been compressed 4d of distance, so it's going to be 4d squared. Don't forget to square both the 4 and the d. And then next we're going to go ahead and just combine these two terms here. So we have 12 mgd sine theta is equal to, so 4 squared is 16, divided by 2 is 8, 8kd squared. One of the d's will cancel out. We're going to divide 8 on both sides. We get 3 over 2 mg sine theta equals to kd. We're going to divide d on both sides. So the spring constant is equal to 3 mg sine theta divided by 2d. Part C, figure 6 shows a graph of the energy of the system as a function of the position of the block from x equals 8d to x equals 12d. The spring potential energy US of the block spring earth system is shown on the graph. On the axes shown in figure 6, do the following. Sketch and draw a line or curve that represents the total mechanical energy E for the block spring earth system as a function of the position of the block from x equals 8d to x equals 12d. Part 2I. Sketch and label a line or curve that represents the gravitational potential energy, UG, for the block spring earth system as a function of the position of the block from x equals 8d to x equals 12d. From part A, we know that the total mechanical energy in our system is 12 E naught, and that is going to be constant because there's no external net force doing work on the system. The problem at the beginning mentioned that there was no friction between the block and the ramp. Next, we're going to draw the line for the gravitational potential energy. And at position 12d, there is 0 gravitational potential energy because we've set that as our 0 reference line. And this is the gravitational potential energy will be a line because gravitational potential energy has a linear relationship to the height, and the height has a linear relationship to the ramp distance. And So the question is, where is this gravitational potential energy at position 8D? So let's start with our gravitational potential energy equation, which is mgh. And the h, we've shown using this triangle and some trig that the height is equal to the what I'm calling the ramp distance sine theta. And so we're going to substitute that in here. And then so from this, we see that the gravitational potential energy is proportional to the ramp distance. And notice that the other variables are all constants. Theta constant, g is constant, mass is constant. So we have this proportional relationship, and using this proportional relationship, we're going to set up these ratios. And so we know that at the highest point of the ramp, where the block is at position 12D, it has 12 E naughts of energy. So then the question is, when it's at 4D, position 4D from the reference line, so I'm counting from the bottom, even though it's 8D is counting from the top, 4D is counting from the bottom of the ramp, divided by the energy at position 8. So this is the gravitational potential energy at position 8. So notice that the 12 cancel out, the D's cancel out, and the potential energy at position 8 is equal to 4E naught. So we're going to start at 4E naught and then draw a straight line all the way to 0 at position 12D. Part D, indicate whether the speed v9d of the block at x equals 9d is greater than, less than, or equal to the speed v8d of the block at x equals 8d. Justify how your response is consistent with the energy lines or curves that you drew in figure 6 in part C. Because the total mechanical energy is conserved, the total mechanical energy at 8d will be the same as the total mechanical energy at 9d. At both locations, the total mechanical energy is going to be 12 E naught. At 8D, we know that the spring is not compressed, so it has zero amounts of energy. The gravitational potential energy, which we just solved, is going to be 4 E naught, which means that the kinetic energy has to be 8 E naught because they have to add up to 12 E naught of energy. Now, at 9D, we know that the gravitational potential energy is going to be at 3 E naught, and we can see that from our graph right here. And at 9D, the spring potential energy, to me, it's a little bit unclear. It looks like it's a little bit under 1 E naught, but it's not super clear. So I'm going to first assume that it's less than 1 E naught, and then mathematically, I'm going to prove that it really is less than 1 E naught. Okay, so then if it's less than 1 E naught, let's think about this for a second. At position 8D, the spring potential energy plus the gravitational potential energy add up to 4 E naught. At position 9D, we have 3 E naught plus less than 1. So this is less than 4 E naught. So the total amount of energy here is less than over here, which means that the kinetic energy needs to make up for the difference. So which means that the kinetic energy has to be greater than 8 E naught. And if the kinetic energy is greater than 8 E naught, that means that it's going faster because the kinetic energy is related to the velocity. And if you have greater kinetic energy, you're going to have greater velocity. So the answer we're going to check off is this first one right here, that the velocity at 9D is greater than the velocity at 8D. However, I was mentioning that this looked like it's kind of close to 1 E naught, and I didn't just want to assume, I actually want to calculate that. I'm thinking that if you just assume this is less than 1 E naught, you probably got the point for this part. But let's go ahead and calculate just to see if it really is 1 E naught, if we can show that. So the spring potential energy at 9D is equal to, and the equation for spring potential energy is 1 over 2kx squared. So if we plug in D, why am I plugging in D? Because at 9D, the spring is compressed 1D amount of distance. So that's why that's why I'm saying that the spring potential energy at position 9D is 1 over 2 kd squared, because that's how much it was compressed, a d amount of distance. And then the spring potential energy, and we know that the spring potential energy for 12D is equal to 1 over 2 k And at 12D, it's compressed 4D of amount of distance. So it's going to be 4D squared. And 4 squared is 16. 16 divided by 2 is 8. So we get 8KD squared. And we're going to set up some ratios to solve for the potential energy, the spring potential energy at 9D, because even though I have this number, I have this value here, it's not in terms of E naught. And notice the graph is in terms of E naught. So at position 12D, I know that the spring has 12 E naught amount of energy. So I'm going to equate this 8KD squared, equate that to 12 E naught. And then we're going to set up this ratio. So then I know that at position 9D, the spring potential energy is 1 over 2 KD squared, but I want it in terms of E naught. So I'm solving for the spring potential energy at position 9D. So U9D is going to equal, and I cross multiplied, and then I move the 8D to the other side, and here's what we get. We get 1 over 2 KD squared times 12 E naught divided by 8 KD squared. Notice the KD squares, they cancel out, and that leaves us with, we have a 12 divided by 2, so that's going to be 6, and then 6 divided by 8, so we get 3/4. And then we still have the E naught right there. So the gravitational potential energy at position 9D is equal to 3/4 of E naught.